Hello dear students, I welcome you in this lecture series once again. This is the lecture series on modern physics which I am doing with you. And so far we have covered some basic mathematical principles which are very important to get into deeper understanding of Maxwell's equations. We have talked about the vectors and their properties and a bit of vector calculus. Without that, we'll not be able to give a meaning to the proposal of Maxwell. So in order you understand Maxwell's equations and how they work, you need what's called as vector calculus. So that's what was the discussion of our previous lectures mostly. Now, today, before we get into Maxwell's equations, they're not only purely mathematical because they have been proposed after thorough experimentation. There were lots of experiments which motivated Maxwell to propose those equations. Today we'll try to bridge those beautiful discoveries. I mean, the idea of the charge and current and magnetic field and electric field. We'll have a journey of experimental foundations of electromagnetism that leads us from Coulomb's law to Maxwell's. So that is the motive of today's lecture. So that is what I am going to discuss today with you. But one thing I would like to keep here, one that I would try to remark here, I would try to say here is that remember the first big work in physics was done by Newton through his book. He published a book called Principia Mathematica. He discussed mechanics in that book. He discussed gravitation and optics. So even Newton had no idea about how electromagnetism works, how charges work, how magnets behave. They have a very qualitative understanding. So there is some attraction, some like you rub these amber rods and they attract pieces of matter. But a quantitative understanding was lacking. It was after I think around more than 100 years that we really knew how charges and their interactions. This is very important because some people think that electromagnetism is older than Newtonian mechanics. That's wrong. So it came late after. No, it came really after some time when Newton proposed his ideas. So that timeline we are also going to cover during this lecture. So let's get into the business. So the first thing is that, can you tell me what's charge? Right? What do you mean by electric charge? And what is fundamentally a charge? So basically, the idea is that you start from a Greek experiment that, you have an amber rod, you rub it, and then it has some property because of which it attracts pieces of matter. And we say that this is electrified, this rod gets electrified, and that we call as charge. Right, so the word electron actually comes from the ancient word amber, right? And then that lightest stable particle known in nature is given the name of electron, and that is actually the fundamental unit of charge. Actually, if you look from the physics point of view, that's our fundamental unit. So the question is, what's charge? How do you define it? Right? Now you define it like it's the fundamental property. It's the fundamental property of what? Of matter. And what's matter? Now that's what was in the Newton's proposal in Principia Mathematica. That matter, what is matter, right? It is, some matter is defined through a concept called density and volume and kind of thing. But it is mass is nothing but it is matter. A quantity of matter, we call that mass. So Newton linked the idea of matter to mass. And that mass, is actually is in Newtonian sense, it is a resistance to the external effect. How do you quantify mass? That the way only I quantify mass is that I see how it behaves under the external influence. I apply force on mass and on matter, and it resists the external effect. And how much it can resist that external effect, that's how small its acceleration would be. That would define us how much mass is there. If the acceleration is very large, the mass is very small. This is how the idea of mass came, how the idea of mass was actually proposed by Newton. So what I said is that what is charge? It is the property of the matter. And what is matter? So that matter is the mass is some quantity of matter like that, and so it's a kind of a cyclic definition. But we should give up that. We should not say that charge is the fundamental property of matter. The more precise definition would be that charge is the fundamental property of mass. So you cannot have charge without mass. Anything that has mass can have charge, right? Or it may not have no total charge. There could be fundamental particles which are chargeless. There are actually fundamental particles that are chargeless. Okay. So it all, then Benjamin Franklin, you see the dates you see here, it is 1747. So then he quantified that there are two kinds of some nomenclature, some positive charge, negative charge. So you could verify that there are two types of them, right? So a body could be positively charged. This was because there are two kinds of forces, that two charges can repel or they can attract. So this is only possible if there are two in nature. So then you label them as positive and negative. But today we know that we have a deeper understanding. We know electron is the fundamental object which is charged, fundamental particle, and which is stable and which we can control in experiments. In our experiments devices, we control this flow of electron only. You cannot manipulate protons, and they are bound inside the nuclei. So when you say that some body is electrified, then either it has excess of electrons or it is deficient of electrons. If it is excess of electrons, then it is negatively charged. If it is deficient of electrons, then it is positively charged. That's what we mean by a body is charged or not, or if it is positive or it is negatively charged. Then, of course, since electron is the lightest stable particle that we control in our laboratories, so therefore, we say that the charge is quantized. That means you can, if you want to charge a body, it can have integral multiples of electrons, right? It can have 2 electrons, 3 electrons, and so on. It cannot have their fractions. So that's what quantization means. And this charge is only conserved. You can only move it from one place to another place. You cannot create it or you cannot destroy it. That's what we mean by conservation of charge. Okay, good. Now the question is, how do these charges interact through empty space? So for that, this man, French physicist and engineer, he invented what's called as torsion balance, a very sensitive instrument which was used to verify what's called as the force between two bodies. And it was done, this was a very precise measurement, only around 2% of error was their margin of error. And he published his work in 1785 somewhere. Some people, there is a conflict a bit that when it was exact date when he published it. And so it's between this 1785 to 1791 when he published his work. Let's focus on this beautiful experiment. This is the experimental setting. And you can see that, this is a very thin thread. It is so thin, like as thin as your hair. So this thin thread, and to which we connect a rod, and there are 2 spheres. And this sphere is charged, and then we have another sphere. And because of the charge, because of the same charge, this could deflect the torque because it's very sensitive, so it will be easily deflected. You can measure the angle of deflection, and then you can quantify the force. So that is how he was able to measure Coulomb force. Now, since these are spherical bodies and they are reducible to point charges, spherical bodies, electric field is same as that of a point charge. That's why in proposal the idea is that there are 2 point charges. And he measured to a great precision in that time. I mean, this instrument was a wonderful instrument. And to Coulomb's surprise, the form of the law was almost similar to that of a law of gravitation of Newton. I mean, this was quite surprising. And also the conflict that how 2 charges interact and there is nothing in between them. Again, you need that concept of a field. Otherwise, you don't make sense. It doesn't make sense. How can 2 bodies interact magically unless there is something in between them? So he proved that this force between the 2 charged bodies, which naturally also have mass, because you cannot have charge without mass, they interact through 1/r² rule. It means that if you double the distance, then the interaction drops by 1/4. And it also depends on how much they are charged, the product of their charge. But remember, the charges that Coulomb considered were point charges. This rule is applicable to point charges. He mentions it. And point charges don't exist in nature. I mean, point charge would mean that which has no dimensions, which is is truly having no size. But the idea would be like if you have a spherical charge distribution at far distance, it acts like a point charge. And if you're very, very small sphere, it will be a very close approximation to a point charge. So now the Coulomb's law is there. So let's build up electrostatics, right? And definition of the charge would be something like, now we can define charge as initially we defined it as property of matter, fundamental property of matter, but now we can measure the force, so we can redefine it that charge is something that experiences electric field. And what is electric field? It is the electric force, it is the influence that one charge has in the presence of the other charge. So you see how complicated things get. You just define one thing, that you modify that definition depending upon what you have discovered, right? So now this concept of charge will become more, it will get its own life, right? So now we redefine electric charge. What is electric charge? Electric charge is the property because of which a body, a mass, experiences electric field. And what is electric field? It is the influence created by a charge. Any charge can create a sphere of influence, the electric field, and any other charge, we will say that body is charged if it experiences that field. Okay, good. So, but suppose you have 3-point charges, then will Coulomb's law still apply? So how do I know that if there are 3-point charges, that now the force between these 2-point charges is not affected by the third charge? How do I know that? I don't know that. I don't know whether it will be affected or not. So the only experiments I will see that if my results, if I apply the Coulomb's law, if it does not work, and I see that if there are 3 charges and I do some mathematics and see that there is no influence of a third charge between 2 charges, and I can do some experiment and prove that that effect is not there, then I will be happy. I will say though that these forces, these interactions only act pairwise. There is no 3-body kind of interaction, right? So for that, it appears that you need one more fundamental axiom to introduce in the system, in the theory. Then you can construct the electrostatic theory. So that concept was the concept of superposition. The need was that if you have many point charges, how will you deal with them? Because your Coulomb's law is given only for 2-point charges. What about 3, 4, 5, or n number of point charges? How would you deal with them? So you deal with them, you have one more presumption, one more assumption, you introduce a principle, you say that, okay, Coulomb's law is there is one more axiom needed, one more principle is needed, one more fundamental rule is needed. That is that 2 charges are not influenced by the presence of the third charge. And the superposition principle works in electrostatics. That means if I have many charges, I can calculate their effect pairwise and take the vector sum of the effect of one charge due to all the charges, and that is what's called as superposition principles. So we avoid that 3-body, 4-body effects are not there, and it's purely a 2-body interaction, and start developing the ideas of electrostatics. So in electrostatics now you have 2 fundamental rules. One, we have Coulomb's law, and the other, we have superposition principle. See, Coulomb's law was it's an empirical in nature, because it was the experimental fact, that was written in the form of a law. Keep it in mind, it was motivated by an experiment. It was not just you were this Coulomb was sleeping and he got some thought about and he just wrote it down. No, it was empirical in nature. There were numbers. He was trying to fit those numbers, and he proposed that rule. The law, because he did not understand why it is the way it is, right? Why it is 1 by r square, why it is the product of charges. This nobody can explain. This is the mechanism with which the nature works. It's a mechanism of nature. You cannot prove it. It's not provable anyway, right? So, I mean, Coulomb cannot prove it because he did not understand the mechanism. So he said it's a law of nature. So just you accept it without any mechanism. And that one body interacts with the other body. Why? I don't know. Maybe what I know is that what is the force between the two charges, and the proposal is that it is F is equal to Q1 Q2 by R squared with some constant depending upon the reference units. And then we have this law of superposition, because the principle of superposition, because we see that, okay, Coulomb's law is valid for 2-point charges. What about if there are many charges? How would I deal with them? So there could be 3-body, 4-body kind of forces, and I will spoil the show. No, then we have a superposition principle that these forces only act pairwise, and we can take a vector sum. So that's where we are now, right? So this is what this is the mathematical statement of superposition principle. It says net force is vector sum of individual forces. Each pair interacts independently, valid for discrete and continuous distributions. We'll talk about charge distributions a bit later. Empirically verified to the extraordinary precision. That's very important. It's not that you say that superposition principle works. It works because it's experimentally provable, right? When you match your numbers, they're exactly what you find in the laboratory. So it's not like if they don't match, then we can suspect there could be 3-body, 4-body interactions, but they're not there, right? Because only 2-body does our job. So therefore we say, our principle is valid, right? So, and it is the superposition principle is actually the foundation for the classical electromagnetic field theory. You will see that why this is so important as I keep in the coming lectures, as I carry on the discussion on electromagnetism. And it is very profound principle, and not discuss too much here. We'll just go to the next idea. So now, after doing a bit of electrostatics, let's get into something magnetostatics, right? Let's get into magnetism, right? So electrostatics, the charges interact, and then the force between the charges is given by Coulomb's law, and Coulomb's law is amazing. And then we have the law of superposition. You need the principle of superposition, and you need at least these as 2 inputs to construct an electrostatic theory. Now, come on, give me any charge distribution. I will use these 2 principles. Suppose you have a distribution of charge, you have a line charge. How would you use idea of Coulomb's law and superposition? You will cut that into small pieces, and each piece is like a point charge, right? And then you will find effect of one piece at a point, right? And then you will vector sum all the effects, and that is superposition principle. So you are taking Coulomb's law, and also you are taking superposition principle, and in that way it may give you a tough time, because you could have an ugly distribution, and when you have an ugly distribution, you don't know how to add vectors in that distribution. That really is the headache. But in a given simple problem, say a straight conductor, a spherical charge distribution, or a circular charge distribution which is uniform, you may apply this. You may have the robust mathematics. You can even do these problems analytically. You don't need even numerical methods. You can do these problems analytically and find the solutions. But remember 2 key points: the Coulomb's law and the superposition principle. It takes it completes our story. So now let's get into magnetostatics. We now get into magnetostatics. Try to understand the magnet experiments related to magnetism, and then we will club the ideas, right? So there was an experiment by Oersted, and it was just you have a current carrying conductor. I know by that time we had these batteries and we could make charges to flow. Now you have a current carrying conductor. Remember now we are in 1820s. We start from 1785. Now the timeline is 1820s, almost around 40-50 years later, right? So now this experiment is that you pass these charges. Now we can control the flow of charges through wires. If you pass current through a wire and put a compass needle, take a magnet, a very small magnet, in the vicinity of that wire, it gets deflected. And this is magical, right? It means that current also is a kind of magnet, right? The current passing through the wire produces a magnetic effect, because otherwise compass is only deflected near a permanent magnet. Now, for the first time, it is deflected by a current carrying conductor. So this was a wonderful experiment, and it revolutionized physics, because you will see that most of the devices later depend on this kind of principle, right? So the basic idea that take away from this experiment is currents affect
compass needles. So remember, this is very, very important statement. Currents affect compass needles, and electricity and magnetism. There were two different phenomena, right? They appear to be connected, right? And this is wonderful. And then it is quantitative. This is the experiment where we have a qualitative understanding that magnetic field is produced by a current, but we have a quantitative measurement, and that measurement is given by Biot-Savart's law. Right? What's Biot-Savart's law? It was again proposed in 1920s, and it says that it can exactly measure the magnitude of that magnetic field due to a small carrying conductor, which we call as current element, and that is the current element, current into length. Right, and it's just like magnetic charge, right? So because if you see that if you take this as charge, then the magnetic field is proportional to 1 by r square kind of a term. It behaves almost like an electric field due to a charge is q by 4 pi epsilon r square, and here it is like, no, this is like a magnetic charge divided by r square term. Right, and you can find you take a small element, right, which is kind of a magnetic charge, call it a current element, and what is its effect at any point at distance r from this, and it turns out that is given by this rule, which is experimentally verifiable, and this rule is called the Biot-Savart's rule or Biot-Savart's law. This is the basic law of magnetic effect connected to a current. It looks like Coulomb's law, almost a similar kind of thing, right? So it also has constant mu naught by 4 pi. Again, these constants are normally depending on which kind of reference units you are fixing, right? We'll not talk about them. Fine, we'll be more interested in what physics is going on. Also, you learn that this force is not radial, unlike Coulomb force. You have two charges, or you take a point charge and put it in an electric field, it will radially be affected, right? So it experiences force along the line joining the two charges, right? But here you can see that the force the magnetic force is normal to the plane containing the magnetic charge and the r direction of the r vector. So it's normal to this r vector and this what's called as current element, and it depends whether it's going in or it's going out, depends on the direction of the current, right? And then we have a beautiful result about this magnetic field, which is passing through a current, which is passing through a wire. We have a beautiful result that if we take, mathematically speaking, if this magnetic field is going around this current carrying conductor, so it has a circulation. It's a property called a circulation. So I can write that what magnetic field at any point and take a dot product with the length element in that direction and keep adding, and it tells me the information about the current passing through this loop. And this is, you see, the current is passing through a loop is something local phenomena, local effect. And it connects, this idea of Ampere's loop connects to the global effect, right? So current is passing through a wire, and I want to see that what happens along this line going around the wire, right? So something at the boundary, kind of a boundary that I choose, the Amperian boundary. So that connection comes through this rule, and it's called Ampere's circuital law. It tells me that path integral of magnetic field over a closed loop depends on how much current is passing through that loop, and where the current is, that's not important, right? Whether it is at center or it is not at center, that's not important. So important is that how much current is passing through. And this is a very, very important generalization, and you will see that this is actually it helps us a lot in looking at the current distributions, which otherwise would be very difficult to track with the Biot-Savart's law, right? But this provides a quick handle. It provides as a method to work out magnetic field. If there are symmetric current distributions, we can employ this integral and quickly work out the nature of the magnitude of the magnetic field. And we'll talk about this rule that there is a curl. Curl means that there is a circulation of the magnetic field, and that is connected with the density of the current. And current density, we know, is that current by area thing. And so we'll talk about this rule in detail once we get into Maxwell's equations. And right now we are trying to cover all the experiments, right? And then comes this person, Michael Faraday. And I mean, he's the most influential physicist known. And he was working in a bookbinder shop, and he never formally attended school of physics, but he was taking notes in these seminars of these big people. He used to attend the Ampere's lectures, the person who invented the laughing gas, and he actually died with that laughing gas. So he later on became his assistant and actually replaced him. He was a very influential physicist of his time. And then his problem was that he did not have mathematics training. So he was not able to express his ideas mathematically. Most of his work is, if you look at his papers, and they're more geometric in nature. You will see all those lines of force in his papers, but that mathematical flavor is missing. And that whole mathematical flavor came when Maxwell proposed all these ideas in a concise way. But his power, his intuition, his visualization was extremely strong, and he revolutionized our physics because it was his experiment, that really changed the course of events in physics. Okay. So he was more obsessed with the lines of force and visualization of fields. So the experiment that he demonstrated, and this experiment is the experiment in physics, one of the most cherished experiments of physics, as good as your double slit experiment, right? And in fact, it's a revolutionary experiment. And what he did was very simple. We have a solenoid, and when you pass current through the solenoid, then it behaves like a magnet, right? So it's like a magnet. And then you have another solenoid, right, that's connected to something that can measure that current is coming or not. So in today's experiment, if you do this experiment in modern labs, and there would be kind of what's called as ampere meter or ammeter, right? So there will be kind of an ammeter. This is an old setting of an ammeter, right? So now what he did is that for the first time he showed that if you move this electromagnetic in and out of a coil, right? So you are moving and without touching anything, and the current is established in the secondary coil, right? And it was the magnetic field, in a changing magnetic field is creating current in the coil, which means electric field is produced, right? So it was initially, what did we see? We see the current producing magnetic field. Now what do we see? We see the magnetic field producing current, the reverse of that. And that is crypted in this equation. It says that there is an electric field. It's actually EMF, and it is the integral of E dot dl. That would be the electric field. But anyway, it is the EMF. You can say that somehow EMF is related to electric field. It's equal to the change of flux with time. The negative sign is because of Lenz's law, what we call as. And if you put the magnetic flux in terms of magnetic field and EMF in terms of the electric field, this would be the equation, which in simple terms tells us that electric field has one more origin. So we learned where from electric field comes. Come on, it comes from a static charge. If you have a charge, it has an influence, sphere of influence. It can affect the other charge. But now he is saying you that without charge, you can create an electric field. You have another source of electric field, which is what? Which is if you have a magnetic field that is changing. So a changing magnetic field would produce an electric field, and a charge will produce an electric field. But changing magnetic field produces an electric field which can curve around. But an electric charge produces an electric field which will not curve, which has no curl, right? So they are fundamentally two different electric fields, right? And one is conservative and other is non-conservative. And question is, what will electric field revolve around? Suppose I have a magnetic field which is changing. What will electric field? It will circulate. It will produce closed lines. But around what? Around that changing magnetic field. If the magnetic field is changing like this, the electric field will be like this, right? That's why it creates current in the solenoid, because it drives the electrons like this, right? And creates the current, right? And this was very, very important experiment. And it was the foundation of what is now called as electromagnetism, right? So I hope you understood all these pieces of information, all these beautiful experiments. We started with Coulomb understanding.
right? How the 2-point charges interact. Then we introduced the concept of superposition principle. Then I took you to the idea that currents produce magnetic fields, and how do you measure that magnetic field? Use Biot-Savart's rule. And then this magnetic field, which is produced by a current carrying conductor, also obeys what's called as Ampere's loop rule. That if you take an Amperian loop and take magnetic field and integrate around a closed loop, that is directly proportional to what currents are going on inside, without bothering about what is the distribution of that current, right? So then you see, normally what do you do in high school? People teach you, you learn about Coulomb's law, then immediately you are told that there is Gauss law, right? But now I connect those important timelines, and so I introduce it. When did we introduce Coulomb's law? What was the timeline? It was 1785 something to 1791, right? That is the period when the Coulomb's law was proposed. That experiment was refined, and all that. Those things were published, and they took time. It takes some time to get good work published those days. But remember, now the date is 1835. When we already have Ampere's law, we have Biot-Savart's law and Faraday's law, and then it is 1835. So almost more than 50 years later, the Gauss law was proposed. And Gauss law is more fundamental than Coulomb's law. You actually can derive Coulomb's law from Gauss law. Of course, you will say, okay, I can derive Gauss law from Coulomb's law, but that's not a very profound result. Gauss law is more profound, it's more general, more natural, because you don't worry about point charges. You forget about point charges, right? Because it works for any kind of charge distribution. You have a surface, what you call as Gaussian surface. It tells me the flux through that surface is proportional to charge inside. And I don't worry whether they are point charges, they are any ugly charge distribution, doesn't matter. It connects again a local effect, what is inside, to something global, what is happening on the surface, right? And then you could have a complicated charge distribution, and if it has some symmetry, then in one shot, you will be able to figure out what is the electric field. You don't need that mechanism of dividing it into pieces of these segments, and then applying superposition and getting into those nasty integrals, cancelling some components, adding some components. You don't need that madness. You can do it in one stroke. So that's how this law gets more profound. But then you will say, oh, it's not about flux, it's about flux, not about electric field. Yeah, it's about flux, then what? But in situations where, flux is also a very important measure. It connotes the meaning of the field itself, right? Well, remember that this is the flux from where you can calculate the divergence of the field. It's a very fundamental idea that connects you to the field, all right? So you talk about flux, but the flux is about the field only. Right, and what is the field at a point that you can easily extract from Gauss law, provided there is some symmetry. There is some symmetry, it will be very easy to work it out. So that is the form of the Gauss law, that the flux through a closed surface is charge enclosed in that surface divided by epsilon naught. It relates electric flux to the closed surface, closed charge, and closed charge, right? Differential form is that del dot E is rho by epsilon naught. We'll talk about it when you come down to Maxwell's equations. We'll talk about that divergence is equal to the charge density divided by epsilon naught. That actually is your Maxwell's first equation. And remember, it's more fundamental than Coulomb's law. So legitimate question is that derive Coulomb's law from Gauss law. And if you derive Gauss law from Coulomb's law, that's an illegal question, right? So you can always propose Gauss law. It is actually the property of 1 by r square function that, because the Gauss was mathematician, the Gauss law will work also for gravity. Newton's gravity. Not maybe GR would be a bit, I don't know how to put it, but in Newton's gravity, because it's 1 by r square thing, and this law will again work there. It doesn't matter whether it's Coulomb's law or Gauss law. It's actually a mathematical result that flux through that closed surface would be the charge by epsilon naught, right? But I can use and derive law of gravitation if I know there is something called gravitational charge, which I call as the mass. So I can work Gauss law for gravity also, right? So good one. So this is Gauss law is very important and it's more fundamental. And when you have Gauss law, you don't need to talk about Coulomb's law because you can derive that. So if I start with Gauss law, I will forget Coulomb's law because I'm anyway talking about Coulomb's law. When I talk about Gauss law, I'm talking about Coulomb's law, and I can use this Gauss law to mint the first equation of Maxwell. So let's get into this slide. I want you to get into it. So why Gauss law is more fundamental? I want to just read this slide properly. It has general validity, works for any charge distribution, contains Coulomb's law. We can derive Coulomb's law from Gauss law. Has beautiful geometric insight because you have flux and it has a flux perspective. And then conservation is embedded. Yes, that is a beautiful idea. Gauss law embeds conservation, where in Coulomb's law you need to derive that rule. How it embeds? It says that flux through a surface is proportional to charge inside. So if the flux decreases, so charge has gone somewhere, right? So the drop in flux is that charge has moved somewhere. So therefore it embeds this idea of conservation of charge, right? So from Gauss law you can figure out this conservation of charge equation in one step. So that's how it works, right? And one of the deeper understanding is that one of the deeper insights is that it is relativistically invariant. Means then that you choose any frame of reference which is inertial, right? You will observe the same law. But with Coulomb's law, you will have a trouble. You will be in trouble. So Gauss law, no trouble, right? But of course, we never talk about invariance of relativistic invariance of Coulomb's law. But what we talk about is the relativistic invariance of Maxwell's equation. And those equations contain Gauss law. And that's why we say Gauss law is relativistically invariant. Keep this is a very important, profound idea. Please keep this in mind, because my next module is all about special theory of relativity, and these ideas will be again thrown to you at that time. I will see that whether you have kept in mind what I said in these lectures. And Coulomb's law has a problem of specific case only applicable to point charges. Gauss law is of general, it is of any distribution of charges. Of course, you will say, no, I do some problems where I have any distribution of charges and I use Coulomb's law. I cut that charge distribution into small segments, but that is an approximation method. And that is, you're also using superposition, right? So, but here you can directly get into any kind of charge distribution. Okay. So the elegance of the Gauss law is, this is the differential form of Gauss law, and this is its integral form. And there is a global relationship between the flux and the local charge. That's what I was telling. There is a local charge somewhere, some local property, and you connect it to some global idea, that is the flux through the surface. And then it also provides it's the platform for the concept of potential. So it is actually when we introduce this first equation, and then we'll see that we'll introduce the idea of potential, and we build up the beautiful theory of electrodynamics. And this is depending on the kind of problem, these things you do in high school. You take a spherically symmetric problem or a cylindrically symmetric problem, a planar symmetry, and then like a spherical symmetry, you know how to extract the information. I can find electric field, and it is for a point charge q by 4 pi epsilon naught r square. I can find it with the Gauss idea. I can use a Gaussian surface which is symmetric about the point charge and get through some mathematics and take electric field out because it is constant over the surface, constant magnitude over the surface, and then I have to only figure out the area of the surface. That gives me the point charge electric field. So this timeline, chronological development of EM laws. So please keep this in mind, because this is very important. You see that in 1785, Coulomb, inverse square law for electrostatics. 1820, Oersted, current affects magnetic needle. 1820, Biot-Savart's law for magnetic field from currents. 1823, it was actually done in 1820s, and it was published, I think, in 1823. So we have this circuital law for magnetism, that, you know, if you take a loop integral of the magnetic field, it is proportional towards current inside. And then in 1831, Faraday law of electromagnetic induction. It was in 1835, but actually it was published in 1867. To keep that in mind. But its proposal was in 1835. It was this Gauss law. You see, Gauss law, when it's coming after all these laws. So that's what you miss in high school. They just mix these Gauss law, Coulomb's law without giving you the timeline, right? It's very important when Gauss law came and became more general, more natural. And then we have Maxwell's equations in 1865. So after all these results are already there, all these beautiful experiments, the physics is empirically known. I mean, all these experiments are empirical, all these results are empirical, and they have been put into the mathematics, in the coded form, in that mathematical, crypted mathematically. And Maxwell unlocks their mystery, their physics mystery. And when Maxwell does that, he proposes these four equations, which we'll talk in detail. We'll derive them. Actually, you can all directly propose them, but we'll see that how these laws shape into these Maxwell's equations and how it is important to correct the Ampere's law to get into optics. And then there was the great unification of physics. This is the first great unification of physics, where when Maxwell's laws were proposed, what happened basically? Electricity and magnetism got bridged with the Faraday's idea. He unified electricity and magnetism. Maxwell unified three important fields of physics: electricity, magnetism, and optics. He combined them into one theory, and that theory is called electrodynamics. So that is the beauty of this. Is actually your first beautiful unification. You know, you might have seen Discovery Channel and you might have seen different programs that these crazy physics people are after unifying all four laws of nature. But why are they up to it? Why they want to unify the different forces of nature? Because they have seen unification earlier. They're highly motivated by the electromagnetic principles, how different fields, electricity, magnetism, optics, appear different. And then a bunch of equations clubbed them into one field, and we actually want that bunch of equations which clubs all the forces of nature. That's what unification is all about. And then what? When he unified electricity and magnetism, the light pops out. You know, the all understanding of light emerges from the idea of electromagnetic wave theory. So what was the puzzle about light? You know, Newton already, as I told you, he published it, Principia Mathematica. He published something about light. So what was the puzzle in light? In high school, you know, there is some laws of optics are taught to you. Snell's law, you know, law of reflection, law of refraction. Where are the laws? Because you only understand the behavior of the light. There is a fundamental question: what is light? Oh, that's unanswered. That's unanswered. And there is no explanation why these laws work, right? They are laws because you don't understand them. But with the Maxwell's equations, you can actually work on this. You can actually derive Snell's law. You can derive the laws of reflection. That is the beauty. That is the beauty of these equations. In fact, there are some remarks, some beautiful remarks about these equations. One of the remarks is that, was he a god who wrote these four equations? Can you imagine? Is the depth and application of these equations? Actually, in the modern field theory and all these crazy string theories, and the fundamental idea of the fields, of the way how basic principles are derived from this theory only. In fact, you'll be surprised that it was this theory that is responsible for theory of relativity. Einstein proposed his theory of relativity because of this theory, because this theory proposes some interesting problems. And when we work through these equations, we find velocity of light is constant. And that is the postulate in special theory of relativity. And Einstein wanted to have similar kind of equations for gravity. And guess what? He proposes GR, general theory of relativity. In fact, this theory is the cornerstone for modern physics. Right. In fact, all modern physics, you can trace back, you can actually connect it to the ideas that we cherished and learned in electromagnetism. So keep these words in mind, always very thoughtful. So what are the key takeaways from today's lecture? All laws are grounded in experiments. Precision measurements are crucial. Surprising connections are revealed. empirical before theoretical, very important. So it's not that somebody sleeps and cooks a theory. No, there are empirical results that you want to create a logic of those empirical results, and you construct a theory. We have gone from forces to fields, from specific to general, from separate to unified, because that was a unified theory, and Gauss law superiority we also discussed. So this is the electromagnetic spectrum. I will tell you the legacy. The classical electromagnetism completed in 1865. Maxwell's prediction of EM waves was 1865. Hertz's experiment verification came in. He could experimentally verify what Maxwell proposed as a theory. So this time theory was ahead of experiment. It was in 1887. And foundations of special relativity, as I already told you, that the foundations of relativity are in electromagnetic theory, and they are in mid 1985. And quantum electrodynamics gets inspiration from where? Classical electrodynamics, and it is in mid 20th century. And modern technologies are rooted in these discoveries. And from Ampere to smartphones, that was a quite journey. So I tried to make sense of all these ideas. I would like to have a disclaimer here. So the pictures that I'm using in these in this lecture, they have been taken from the web, and the copyright lies with the rightful owners. I am doing it only for the educational purpose. There is no other purpose of using these pictures and diagrams. Thank you very much. I hope you enjoyed the lecture the way I enjoyed it. I will see you soon in my next lecture. Thank you very much.